Welcome back to the Foundations of General Emergence Mechanics. In today's lesson, we're diving into a very precise mechanical question. We want to know, once all our previously established ingredients are actually in place, how does the baseline minimum move? Today, we're going to derive the exact mathematical shift toward our candidate attractor. We have a beautifully structured mathematical path ahead of us. We'll start by building the free energy, then carefully expand around the baseline minimum, derive the shift formula itself, and finally look at our 255-degree target. So let's jump right into the first step, building the free energy. To ground ourselves, let's quickly recall the journey so far. Episode 2 gave us the baseline threefold minima. Episode 3 introduced the chiral bias, and Episode 4 added coherent stiffness as the missing dynamical correction. And we have to remember, those baseline and bias components are physically incomplete without that dynamical restoring correction of the stiffness. They just don't tell the full story until stiffness is in the mix. Right, so this mastery equation serves as our mathematical stage. It represents the complete effective free energy that dictates the system's phase dynamics. As you can see, it brings together our Z3 baseline, the bias, the stiffness, and the closure terms all into one unified framework. Looking at the explicit terms here, we can clearly see the specific competing players. We've got the baseline curvature doing its thing in the Z3 term, the directional pole of the chiral bias, and the stiffness, which mathematically acts as a quadratic response around a preferred center. These are the active forces calculating our shift today. Now that we have our free energy built, let's move on to expanding around the baseline minimum. If you think back to the Z3 baseline term alone, it gave us minima at 0, 120, and 240 degrees. Well, the relevant starting point for understanding the later attractor is that baseline minima at 4 pi over 3, or 240 degrees. So we define the phase this way, where delta simply represents a very small deviation away from that baseline minimum. What we're trying to do now is solve for this small shift, this delta, perturbatively. We're asking, how exactly does the system inch away from 240 degrees? To find that new effective minimum, we need the stationarity condition. Setting the first derivative of the effective free energy to 0 mathematically locates the stable bottom of the energy well. It's the precise point where all those competing forces reach a stable equilibrium. This right here is the mechanical heart of our derivation. By carefully applying a first-order Taylor expansion to each term individually around our baseline, we get to simplify those complex trigonometric functions into linear expressions of our small shift, delta. The Z3 term simplifies to a linear factor of baseline curvature. The bias term gives us the chiral pole near the baseline. And the stiffness term gracefully links our baseline, our shift, and our preferred center together. And that leads us perfectly into deriving the shift formula itself. When we put those first-order approximations together, we arrive at this combined condition. Look at how it elegantly groups the delta terms on one side, driven by baseline curvature, bias, and stiffness, and balances them directly opposite the coherent center displacement on the other. Solving for delta gives us the central shift formula of this episode. Visually, it tells a very clear story. The shift directly depends on how far the preferred coherent center is from the baseline minimum. That's our numerator. And that is divided by the denominator, which is basically the competition of forces trying to resist that shift. Let's take a second to break down exactly what each parameter in this formula means physically. The 9 lambda 3 is the baseline curvature acting as an anchor. The minus 2k is the bias correction, providing a subtle directional pull near the baseline. The lambda represents the stiffness response, acting like a spring pulling the system toward the preferred center. And theta naught is that preferred coherent center itself. They all interplay to dictate exactly how far the minimum will shift. Now, as a mathematically serious course, we need to be intellectually honest here. This derivation guarantees the conditional mathematical mechanism of the shift. It shows exactly how the minimum moves, yes, but it does not independently prove the exact value of the preferred coherent center. Proving that specific value is the job of the full closure program, which we'll be tackling in later lessons. Which brings us to the 255-degree target. If the closure-selected coherent center is near 255 degrees, well, plugging that into our formula mathematically dictates a very specific result, exactly a 15-degree shift. The math elegantly bridges the gap from our 240-degree baseline, shifting it up by precisely 15 degrees. And that makes 255 degrees the absolute central target of the modal theory closure story, even though the complete independent derivation of that exact destination is a further task for later. We've now firmly structured the mechanism that makes it possible. We haven't proven the destination yet, but we know exactly how the road bends away from the baseline to get there.
Let's step back and summarize the analytical ground we've covered today.
We successfully built the effective free energy. We performed our expansions starting at the baseline 240-degree minimum. We derived a perturbative shift formula showing exactly how it depends on curvature, bias, stiffness, and the preferred center. And finally, we mathematically structured the 15-degree shift mechanism, even as we patiently await the full closure proof.
Before we wrap up today's lesson, I want to leave you with a question to ponder. If the shift depends on both the stiffness of the system and a preferred phase center, which of those is actually doing the deeper explanatory work? Take some time to think about that, because understanding the true fundamental driver here is absolutely essential to mastering general emergence mechanics. Thanks for joining me today, and I'll see you in the next lesson.